is that when you get the case that W1 is bigger than 1 and W2 is bigger than 1, depending which proportion you start out with, whether you start out with more little a's or bigger a's, you go to what's called fixation, and that is one of the alleles is eliminated and only the other allele persists in the population. So fixation means that a particular allele disappears, while the other allele is the only one that you'll find in the population. And so this is called disruptive selection. The opposite case that you get is over here, where what it says is the heterozygote is fitter than either homozygote. This is sometimes called hybrid vigor. And so what it says is that if you have two alleles, and they're different, it's better than having two alleles that are the same, no matter what the two are. So for example, imagine one allele gives you an advantage in cold weather and one gives you an advantage in warm weather. And it may be that physiologically you make two kinds of enzymes. One works well at low temperatures and one works well at high temperatures. So if you're only the high temperature kind, then you do well at high temperatures but not at low temperatures. If you're the low temperature kind, you do well at low temperatures but not high temperatures. But if you've got both, you have enzymes that will work both at high and low temperatures. So this is quite common. And another place where it's also common is in something called, well, anyway, I forgot the thought that I had there. So this has got to do with hybrid vigor. So here, there's an example on sickle cell anemia where it says that W1 is 0.9 and W2 is 0, and you build a model, and you can have a look at that example. When you have a model like this, where you've got W1, 1, and W2, instead of getting this very simple model that we got where xn plus 1 is equal to 1 is equal to xn over 1 plus xn, you get a more general case. And this more general case is governed by this formula over here. Now, I'm not going to derive that equation for you. It's actually not that difficult to derive. And it's just a more general process of what we went through to derive the lethal recessive equation. And you can see that in some of the references that I've given you, but this is the model that you'll play around with. But before we end this discussion about genetics, the first is that if you want to see how to derive these models, you can look at these different references here. So there's this chapter by Hastings. It's at the website. You can have a look at Wikipedia, which will use what are called mating and offspring tables and help you derive that formula using those tables. There's also the so-called Hardy-Weinberg principle and deviations from that. So the Hardy-Weinberg principle arises when you assume that individuals mate at random. And so if you've got the Mendelian laws in operation and individuals choose each other at random, then the Hardy-Weinberg principle tells you that if there's no selection going on, the proportion of alleles in the population does not change from generation to generation. There has to be some kind of selection, and by selection what I mean is that you've got W1 and W2 different from the number 1. If W1 was equal to 1 and W2 was equal to 1, then these would all be equally fit, and the Hardy-Weinberg rule says that the proportion of A's from one generation to another, small a's or big A's, remains unchanged. However, you do get things like assortative mating. And assortative mating has to do with the fact that individuals don't select mates necessarily at random, but may select individuals that are more like themselves. Or there's disassortative mating. Disassortative mating says that you should select individuals that are less like yourself. Disassortative mating, for example, is you should avoid incest. So why should you avoid incest? You thought it was just a general rule, but there's a good reason. Yeah. Okay, what's bad about inbreeding? Right. So if I have a recessive lethal, I want to choose a mate who does not have the recessive lethal, because then the progeny will be all okay. But if I choose somebody I'm closely related to, they're also more likely to have a recessive lethal than just at random, because we probably inherited from the same parent. So the inbreeding taboo comes from the fact that it's good to make sure that you choose individuals that if you might have a deleterious mutant just by chance, or deleterious allele, you want to minimize the probability that whoever you're choosing also has the same deleterious allele. So that's got to do with disassortative mating. Disassortative mating is also good from an immunological point of view. Immunology, you have to fight off lots of different pathogens that, and there's great diversity out there. So the more diverse your immunological system is, the better it's going to function. And that diversity can be maximized through finding partners who are less similar to yourself. And what biologists have found, for example, is that the smell of urine is linked to your immune system. And mice choose individuals as mates from smelling the urine and choosing individuals whose urine smells less like their own. So there are all these things that we don't think about, but, and that's probably because we don't have a great sense of smell. But you can certainly see there's probably some assortative mating in human populations where tall individuals are more likely to choose tall mates and shorter individuals shorter mates. I don't know if that's true. Who thinks that's true? Only one person. Okay. You don't think there's any tendency? Like if you're a woman and you're 6 foot, are you more likely to choose a guy 6'3" or 5'6"? I think you're more likely to choose a taller guy. That's a good point. What I'm saying is that it's probably genetic, but I'm guessing. I don't have any evidence for this. Now, humans do a lot of weird things. And before we go on, there's throughout history, humans have. Why is it not there? I just checked it and it was there. Hybrid cats. They're all these. Wow. I don't know why this is not coming up. So people interbreed cats like lions and tigers. So have you heard of hybrids between lions and tigers? So what they do is that a lion and a tiger, if the male is a lion and the female is a tiger, they call it a liger. And if the female is a tiger and the male is a lion, they call it a tigon. Now it turns out that ligers are much bigger than tigons. And there's a website where you can say, why is this true? But the reason for it comes back to this thing that the genes you inherit from your father are different than the genes you inherit from your mother, in that the tertiary structure, called the epigenetic structure, which has got to do with the methylation of the genes, is different, and they're different patterns. So, for example, babies are more likely to look like their fathers at birth than later on. In humans, a baby tries to look like its father at birth. Why is that? Sorry, the father what? Right, yeah. So fathers can't be sure. Only mothers can be sure of their children. Fathers can't. So if a father looks at the child and says, wow, this kid doesn't look like mine, then he might abandon the mother and the child. Now, we're not talking about modern times. We're talking about humans some tens of thousands of years ago, hundreds. But maybe modern times too. In fact, there's some statistic that about 15% of men are cuckolded, and the children that they think are their own are not really. But women can't get away with it as easily now because of genetic testing. So anyway, what happens with lions and tigers is that lions have very competitive mating systems, and male lions, if they take over a female by killing the pride leader, another male, then they'll kill the cubs and they will immediately breed with the female. And this is a very competitive system, and male lions don't stay for a long time. They can be usurped. So what they want to do is they want their cubs to be as big and strong as possible. Whereas a female is not interested just in one litter, she's interested in several litters. So she doesn't want every litter to be as big as it possibly can. So male lions have genes that make their cubs grow fast in utero. And female lions have genes that down-regulate this growth. You don't have that system in tigers. So that means a male lion and a female tiger, the cubs will grow very big, and they'll continue to grow after they're born more rapidly than normal, and so ligers get very big. Tigons, on the other hand, is that a male tiger does not have these genes to promote rapid growth of its cubs, and the female is down-regulating the growth anyway, so those cubs are going to be smaller on average than lion cubs. So you can go to these websites and you can have a look at these things, but this is just to show you that there are issues that go way beyond the simple Mendelian models that we talk about here. And another one is the whole concept of kin selection. And in kin selection, the big problem was, how did altruism get selected? Why would we give up our lives for our relatives? Why would we give up our lives for anybody? Why would we go to war and fight on behalf of our country? And the idea is that there are elements, genetic elements, that make us, that if we are related to close kin like nephews. So for example, an individual may invest in a nephew if they don't have their own kids, and they may be willing to give up their life to protect several nephews or nieces. So people have done the numerics on this. And the reason is that a gene that makes us invest in our nephews and nieces can actually spread in the population, because it's not only through direct inheritance, but indirect inheritance, in that I'm closely related to my sister, and so genes in me are likely to be in her, and anything that helps me raise her progeny can be passed on from me through her, because we're related to those progeny. And this is the way genes for altruism can spread. So if you're interested in that issue, you can go to Wikipedia and look up this whole issue on kin selection.